So today we're going to look at continue to look at Fortran, and we're also going to, in the final part, we look at how you build your software in Fortran in an efficient way, and some of the tools that you use for this, like CMake and Makefiles. So we start off where we ended last time, and there are one type of variables that in subroutines that we need to discuss, and this is so-called automatic variables. And automatic variables are temporary variables that you can declare in subroutines, which are creating in a special memory area called a stack. And the stack is a memory area which is you can add temporary things on it, and when you return from a subroutine, that memory is freed. It's very fast, and so for smaller variables, it's very efficient to use the stack. And these automatic variables in Fortran, they are allocated to the desired size in the subroutine. But of course, they have to fit in the stack, but that is a limited memory area. So we have to be careful a bit about that. So an example of this is shown here. So I have a program here, automatic arrays, which contains a subroutine A here. And I call my subroutine A here with my variable array, two-dimensional array A. And in my subroutine, I need an additional array that is the same size as A. And that is, you can do this without any dynamic memory allocation by declaring the variable using the size here. So you can query the size of A, and query the size of A, the number of rows and columns here, and declare another B. So this variable here will be allocated automatically for you on the stack. And you can use it in your calculations here. And when the calculation is done, the memory for that array or variable is automatically reclaimed. So this is an easy way of providing some additional storage space in subroutines without dynamic memory allocation. So we will continue with more on arrays and how we can work with those in Fortran. So the first thing that is a bit new concept here up until now. So all the examples I have shown before have been, you have static sizes of the arrays. And static sizes is not always possible to do, because you have, for example, input data that varies with the size, and you need to kind of adapt and create arrays depending on the size that you, the problem provided by the user, for example. And in that case, you need to be able to allocate things dynamically during runtime. And you declare these variables using the special allocatable attribute in the declaration. You define the rank of your arrays, but you never define the sizes of the bounds until you allocate the array. There is a special statement called allocate in Fortran that you can use to create memory area for these variables. Before Fortran 90, it was not possible to do this. This was not part of the standard. So in Fortran 77, you always needed to create fixed sizes of arrays. You could come around this by specifying so-called work arrays, basically really large arrays that you declare in the beginning of your program, and you use that to store your multiple arrays. So many programs had this kind of mechanism to create and allocate in a single array different arrays. But it was cumbersome, and you still had to specify in the source code the size of the work arrays. With all dynamic memory, you need to be able to deallocate memory. So when you don't use the arrays anymore, you have to deallocate them. And there is a special subroutine called deallocate that you can use to remove tell the operating system that you don't require this memory anymore. Also, there is another feature in Fortran, actually Fortran 95, is that if you allocate arrays inside a subroutine, you actually don't have to call deallocate, because an array that is declared as allocatable in a subroutine automatically is freed when the subroutine or function returns. But it doesn't hurt to kind of deallocate explicitly, because that's doesn't make the code any different. But it's good to know that subroutines handle this automatically. Sorry, wrong direction. This trigger. So how does it look in code? So here in example here, I declared a floating point variable here, and as usual, you can declare it with a dimension like this. But instead of specifying the exact size, you provide a colon for the rank, first rank here in this case. And then you can also move the parentheses to provide put it here as well. So you don't have to use the dimension here. And if you have a two-dimensional array, you specify colon, comma, colon, and then or parentheses colon, comma, colon after here. And then you have this allocatable attribute. And that tells Fortran that this variable is allocatable, can be allocated. And then you have the statement here, allocate, which is used to create the actual memory area for your allocatable array. So up until you do an allocate, the variable is undefined, and there is no memory associated with it. So if you try to use a variable that hasn't been allocated, you will get a hard crash of your program. Segmentation fault, or in Windows terms, it will be access violation or similar. And here you also allocate two-dimensional here by specifying the sizes here, 20 by 20. And after this allocate statement, the variables can be used. Same rules apply here. I haven't assigned anything to them, so they're still undefined, but you can still use them. So the memory areas available, so you can assign values to them. And then when you are done with your program, you can do deallocate, and then you just specify which variable you want to deallocate. It's also possible to, instead of doing multiple statements here, you can have a comma here and add multiple variables here that you want to allocate. Same thing with the deallocate. So you can have a deallocate that says deallocate f, comma k. That works as well, and that will free up the memory for both of those variables at the same time. Another feature that is added to the Fortran 90 specification is the ability to extract fields and arrays from other arrays. And those sub-arrays can be used as parameters to subroutine calls. And it's very similar to what you do in the MATLAB's index notation, where you can use colons for accessing different columns or rows in arrays. So here's an example of how this can look. I have a 5 by 10 array A, and I just fill it with values here, like this. And then I think I can run the example here instead. So let's see. Okay, this will be different. Okay. So if I run this will print out the entire array, and this will print out just the one first row and 5 by 10 columns here. And you can have also the two-dimensional specification here. So 1 to 5, 5 to 10. This will be a two-dimensional array. And you can also specify non-contiguous indexes here as well. There is of course a warning note to this as well. In certain cases here, same thing with Python, Fortran tries to avoid creating copies if unnecessary. But in certain cases here, using this index notation will produce a copy in memory. So it's not necessarily that you can modify the values inside the subroutine and also modify the external. So there could be a copy. And that could be a problem for larger arrays, for example. And this is the output here. Skip that one. It's also possible to do vector matrix multiplication as well. So there is a built-in mapmul function, a comma b, and there's also dot product here for doing scalar products. And it just looks like this. So in this case here, I have 3 arrays, and I want to calculate C here, which is a matrix multiplication of A and B. So you need to make sure that this here is the right size when you do the calculation. Otherwise, you get access violation and segmentation faults. There is no checks done in this case. And then you just call mathmul and then A, comma B. And you can list them in multiple depths as well. Then there are other routines that are useful for arrays. So all will return true if all elements are true. So in this case, this is usually if you have an array consisting of Boolean values, you can use all to check if they're all true. You can also do any here to check if any element is true. There are functions for returning max val and min val of values in an array. You can do product of all elements in the field, sum of all elements. So you can see here there are similarities to Python here as well. So you can see what to do. So you have a product of A, and then you have sum of A. They all return single scalar values. There are also other good functions to use. So L bound and U bound are used to, if you have changed the indexing of your arrays, for example, they started by 0 or -2, you can use L bound and upper bound to return the field index of the lower field or upper field. Shape can be used to return an array of the size of an array. So in this case, it will assign rows, and that you can also use for arrays in your main program as well. So another important thing in Fortran is being able to read and write data in different forms. So reading and writing for files is very similar to what you do in Python. You have a read and write statement for reading data and write statement for writing data. There is some difference here from Python that the read and write statements are always reads one row or writes one row. The first parameter of the write function determines, or read and write determines where to read and write. So if you want to read from standard input or standard output, you put a star as the first parameter. Fortran also automatically converts text into file. So when you write floating point values, the conversion to strings are handled automatically. So you don't have to explicitly convert to a string before writing as you have to do in Python. In Fortran, that will be taken care of automatically. You can also read several variables at the same time in a single statement. And then you have separate the values in the file with commas. And the decimal point is always a dot. So there is no comma in the decimal. So there's always a dot in Fortran. And also, if you have a lot of values you want to read in a single line, you can in a similar fashion as in Python, read using a special implicit loop inside a read statement or write statement. So in this case here, you can read. I want to read 8 floating point values from standard input. You can see here I have a star here. That means that is reads from standard input. And here you see here I have specified the array values directly I want to read into. So this read statement expects you to have 8 floating point values separated with commas in the text file. But if you have more than 8, it can be cumbersome to kind of list all of them. Then you can create something called an implicit loop here inside your read statement. So in this case, it will use a loop from 1 to 8 and read AI from the file directly. And you can use the same procedure for writing here. So in this case, I write to standard output, the screen, and then I specify implicit loop to write the data to the file, and then the commas will be added automatically. If you just want to print things to the screen when you're writing your code, there is also a print star statement here which you can use, which is a simple form of just getting things to produce something on the screen for debugging, for example. Sometimes, I mean, by default, if you don't specify, there are two parameters here. So there is the first one is the direction where to write. The second one is the format. And if you provide a star in the format, Fortran will always try to represent the number by the highest precision in text file format. So you get really long text strings that represents the floating point value. And the second parameter defines, as I said, the output format. And if you just do a star, it will kind of just do full precision. But you can, just like in Python, when you do formatting statement, you can actually format the output by this second parameter. And you use very similar codes in Python for defining the outputs. And those codes are called format codes. Common codes, you have A with a number after it, and that is a character string with the width of n. IN, that is an integer with the width of n. So the brackets you don't have to specify, that is just an option here. Then you have J, bracket m comma n, that is very similar to what you have in Python. M is the width of your field, and n is the number of decimals. And this is a generic floating point value. There is also F, which you can use to specify more exact fixed format. You can also repeat the format code. If you know that you have 6 integers with the width of 5, you can specify 6i5 in your format code. And note that you always have to specify the parentheses here, even if it's a string. You have to provide a parenthesis in your formatting code. So this is an example here. I have a header here consisting of floating point values. B here is integers. And here I want to output, first I will write a header. So a header consists of text describing the different columns in my table, for example. And then I know I have 3 fields with 8 character in width. So this says 3A8. So I have here, this is an 8. This is also 8 width, and this is also 8. And then I now have 4 fields with the width of 5. So these are this one here, this one here, this one, and this one. And you see here that the formatting code starts with a quote, single quote, ends with a single quote, so that it's a string. But you need to specify a starting parenthesis and ending parenthesis inside a formatting string. Otherwise, you will get a syntax error from Fortran. And then I want to write the table values here. So in this case, I want to specify, I have 3 floating point here, and I want to present them in a generic floating point format with a field width of 8 and 3 decimal points. Then I have 4 integer values with a width of 5. That represents the following output. So you can see here that I have 4 A's here. So that is a field width of 8. And you see also that I have B's here that are also 8. And then I have 8 here. You can also see that the actual numbering field is exactly 8 characters in width here. And then I have the integers here. You can also see that they are left adjusted here. And I don't think you can adjust that in Fortran. But this is the way you format. So it's very similar to what you have done previously in Python. But sometimes you have a problem with your formatting code because as you have to specify a string with numbers in it, sometimes you need to print something that you don't know the size of. So sometimes you need to create this format code dynamically depending on the input to your routine. For example, if you have a generic routine for writing an array to the screen, the array that comes into the subroutine could have different size, and you need to be able to adjust to that in your formatting code. And what you can do then is you can use a character string in the write statement as a file to write to. So you can use, instead of writing to a file on disk, you can write to a file or a string variable instead. So what I do here, I create a special formatting code string, which will be the format code I will use later on. I reserve a lot of space in it, so I have 255 characters. And you can see here that I have a array coming in here, and I want to print it. So I query the array for the rows and columns. And then I want to create a formatting string that will create the number of columns floating point values in this case. So then I put, instead of putting the direction here, a star, I put format here, so that I want to write to this formatting statement, this string. So everything that I provide here as a parameters into this write statement will go into this formatting string. So that will produce a string that is the size of the array here. So this will be replaced by the number of columns in the array coming in. And then I can use print format here to print out with nice formatting as well. So that is a nice way of handling this. It's a bit complicated, but of course it could be that you can create a subroutine that creates this automatically for you to make it easier. So what if I want to, now all the examples I showed you here will write to screen and read from the standard input. But what if I want to write to file? Then it's actually very similar to Python. There is an open statement in Fortran as well that will create an associate integer variable with a value to file. And the open statement also defines if you want to read and write, just like Python. There are three modes of operation in Fortran, which is also similar to Python. You can write by default to text files, writing line by line to a text file. There is also a special text file mode called named-list IO, and that will write named variable and value pairs into text files, which you can read back again and assign to named variables. And then there is also the unformatted IO, that means binary files. So you can write binary data to disk. A note there with binary files. Fortran doesn't have a standard for what is written to how it's written to the binary file. So if you write a binary file on one system, it's not necessarily compatible on a different system. So just make a note of that. So that could be an issue sometimes. When you have opened a file and we are done with writing or reading, you need to close the file. So it's the same warning I said with Python, and that you need to tell the operating system, I'm done with this file. So the operating system can finalize the writing to disk so make sure that it's written to disk. So how do you open files? So the first thing I do when I have files, I usually create constants for I do basically as a identifier for the file, and usually you give that a number, and I usually create constants for each of these numbers I want to use. So in this case, I have one number for the input file, which is 15, and one number for the output file, which is 16. So then I open here, and the first parameter is the unit, and the unit is the number of the file I want. This number will be used to manipulate this file further on as well. So I provide in file here. I specify the file name here, which file to open. How do I want to open this file? I want to open this as a text file. That is, I will access the lines sequentially in the file. And what do I want to do? Do I want to write or read? So action equal is to read. And then I continue here. Then I use read here. And And I specify the first parameter now is the file unit that I want to use to read from. So in this case, I use infile here to read. I add my variables here that I want to read in, and then when I'm done, I do close here. Now I tell the operating system I'm done writing to this file. Next, I want to write to a file. So the unit is the out file now. Same parameter, I have another file called dot. Access is still sequential, and then I have action write here instead. Now I can do write out file star. So now out file is where I want to write to, and that is this identifier 16. And here I add my variables that I want to write to disk. And then finally, I close the file as well to make sure that the operating system writes the data to the disk again. So in Python, everything the open file will return you a file object, and you operate on this object here. So in this case, the object is the in-file number that you use to tell the different functions for reading and writing where to read or where to write, and that you pass along to different functions. You can, as I told you before, if you have a star, you read from keyboard. And if you have a star when writing, it will write to keyboard. There are some reserved numbers that you have to be a bit careful. These are inherited from Fortran 77 a long time ago. So 5 here is the predefined number for the keyboard. So if you specify a unit number of 5, it will still read from the keyboard, not from a file. You can also, there is a unit number called 6, which is the standard output. There should be standard output here. And also star here is also standard output. So 5 is when reading from keyboard, 6 is writing to the screen or a terminal. A little bit about code structuring. So for smaller projects, you probably don't have to think too much about modularization. It's probably just you write a single file or function, and you don't have to think too much about how you structure your code. But when your project is getting larger, you need to kind of think through how you organize your code so it can be maintainable. And in Fortran 95, just like Python, the key to modularization is the module. So modules is very similar to Python. You can collect a number of functions in a module and group them together and use them together as well. Same thing in Fortran. You can group subroutines and data together as well. So this is a typical code structuring here. Again, from my structural mechanics background. So I have my main program. I divided up this main program in modules called input data, for example, for reading and writing data. No, so reading data from disk into my data structures. I have a module called finite element, FEM, which contains my finite element routines. I have a module called solve that is used for solving the equation system. And I have an output data module for writing data to disk. And in many cases, you have certain functions and routines that are common to all of these modules. Then I also have a utils module here that is used for things that are common to all of these. So how does it look in source code? So in this case here, I have my program stress. And in this case here, I have an input data module, output data module, finite element module, and I just tell it to use all these modules here in my main program, and then I have access to all of these routines, subroutines and functions and data. And then in my module FEM, I use the utils module here, so I have used utils here in my finite element model, and finally have this module utils here that is used by all modules. You can also see here that utils doesn't use any of the other modules. So it's self-contained in that case, in this case here. So doesn't depend on the fem module. More on subroutines. Something that is new in Fortran 95 is that you can also, just like in Python, pass procedures as arguments to subroutines. And you have to define the interface between these to be able to do it. It's a bit more complicated than in Python, because Python, a dynamic language, is much easier to pass functions over, because a function is an object, and you can pass an object over a function call. And you have to declare the type of the function that you want to pass in the specification part. I think it's better to show an example here how this can look. So the goal of this code here is to create a tabulate function here. Just in one of your Python example here, to kind of give a start interval, end interval, and a step. And then the end parameter here is a function. So in this case here, you need to declare this function here inside my subroutine here as well. So kind of tell this to Fortran what the function should look like that is passed into this function. It's very similar to a normal variable declaration, but it's more like I declare how the function should look like, and that is the data type. So interface function func x here. So he describes that I expect a function here that returns a relate. It takes an x variable input here that is declared as a relate. Intent in just tells the subroutine that it's an input variable and you can't assign it out. You can have intent out as well to limit that this is an output variable as well. So it enforces an additional check in the compiler to make sure that you don't abuse this x value. And then you can see here that I have a subroutine here that is identical here. So if these are identical, this will compile together. So you need to declare more when you do this, but it works just like in Python, that you can pass a function over. So in my main program here, I can call tabulate now here. And you see I have declared a my function here in my, so this is the part in the utils module here. I have my function here. So here I can pass this over to the function here, and tabulate knows how to call this function here as well. So here you can see it calls the function here using the name coming in here. So this will correspond to the my function here in the main program. And you get this nice output here. There's also some other very nice features that makes Fortran even more Python close, and that is keyword and optional arguments. So just like in Python, you can specify arguments using keywords, and you can do this in Fortran as well. And the reason for you doing this is that sometimes when you in Fortran, many of these subroutine arguments lists can be very long, and sometimes many of these arguments usually should be called with certain values and could have default values, and then you can add these default values in your code and reduce the number of arguments that you need to call the function with. You can, in your declaration, your subroutine, you can specify a subroutine to be variable to be optional. And that means that user calling this subroutine doesn't have to specify this argument. And you can check in your subroutine if an argument has been omitted. There is a special present function here that you can use to actually test for the presence of an optional argument. And as I said, arguments can specify with keywords. So in this case here, I have my very exotic subroutine called order ice cream. It has 3 parameters: number, flavor, and topping. And integer here is just a normal parameter, nothing special. If you don't give any additional attributes to incoming argument, you need to specify this argument or this parameter in the argument list. Here I said I have two optional arguments, flavor and topping. And I need to, before I can use an optional argument, I need to check for that it is present in the call. So in this case here, I can call this in different way here. So in this case, I have order ice cream 2. I only specify the number here. Then present will be false. So then I said no flavor was given. If I call it with 2.1 here, it will say this will be true and this will be false. And in this case here, both of them will be true. However, if I want to specify the third argument, I can't use the normal syntax here, because if I don't want to specify flavor, I need to somehow leave that out. And if I want to specify topping, I need to actually use a keyword argument here. So topping equals to 3. Then flavor is false and topping is true. It's also possible in Fortran to overload procedures. So you can have procedures that with the same name handling different data types. Python has no problem with that, because subroutine can take any data type as input, and you have to check it inside a subroutine. In Fortran, because it's a strongly typed language, you need to specify the data types in your subroutines. But you can emulate this behavior in Python by using overloading. And that means you declare several subroutines for each of the data types, and then you can combine in a kind of virtual function that calls the correct overloaded subroutine depending on the data type. And you have to declare an interface that defines these calls in Fortran. I think it's better to show an example here. So I have a module here called special, and I want to create a function here that you can use with both floating point and integer values. So in this case here, of course, I can declare two functions here, one called ifunc and one rfunc. Ifunc takes an integer, and the rfunc takes a floating point as input and returns a floating point output. And those can, of course, be called separately if you want to. But if you want to combine them in a single, if they do the same kind of function, you can combine them into a single function called func here. And then what I have to do then is I have to declare an interface called function. And in that interface, I will tell Fortran here, this function is implemented by two functions, ifunc and rfunc, depending on the data type that you call it with. So this interface declaration here will enable me to, I declare two variables here, one integer and one floating point. And then I can call, if I call the function with an A, it will call the integer function. If I call it with a B, it will call the I function here. And this can be shown here. I just illustrate here with two different expressions here. So if I call it with an integer, it will return you an integer. Otherwise, it will return you a floating point value. So this can be very useful to create, simulate the notion of having a function library that can handle different data types automatically, just like you can do in Python. So you have to define the operation. Yeah, I think I will. Yeah, you can also, something that is new also in Fortran 9 is you can actually overload the operators. This is something you see, you have many of the object-oriented language can do this, also do this. In Fortran, they have also provided a way to overload using the normal functions, so to speak. And that enables you to implement actually vector and matrix operations using normal operators. So you can create really sophisticated libraries here with your own, for example, derived data types, and provide operators that you can operate on these derived data types, just like normal expressions in Fortran. So you use interface operator and then to specify here which operator you want to override, and you have to specify the functions implemented these overloads. So usually how you create it's called type as a derived data type function, and then you have the name operand 1, operand 2. So for example, here I have implemented the minimal vector operations library here. So a library or module that can implement vector addition. So I declared here a derived data type called vector that consists of 3 components like this. And I have created an interface here for overloading my plus operator. And what I have to do then is I have to tell Fortran which functions should be used to implement this operator. So in this case, I define vector plus vector is the function I want to implement this operation. So here I create a type vector, a function that returns a vector, and here's the name here, and then it takes two vectors as input. So in this case, v1 and v2, and then I calculate the sum of these two here. So v1 components plus v2 components. I return this as the function here from the function, and that will enable me to use the plus operator with my own vector data type. So in my code here, I add use vector operations like this, and I specify 3 vectors here, v1, v2, and v, and I assign v1 1, 0, 0, and v2 0, 1, 0, and then I can create an expression like this: v equals to v1 plus v2, and that will produce this output here, which is the vector addition of these 2 vectors. So I will do a short break now. Just say we continue 10 past 2. So additional things I want to talk about is a bit about how you can protect this is the start point here. So when you design modules, you can specify certain parts of the modules that you want to be private from the user of the module. You can also set what is public. By default, everything you define in the module is public to the user of the module. So basically what you have to do to make things private is to specify the private attribute. The public attribute is kind of not useful in that sense because everything is by default public. So the idea with this that some of the things that you implement in the module, for example, implementing a simulation model or something, is something that you only need inside the module. You don't need to have it accessible to the user of the module. And that is also to prevent side effects in modules that if you don't expect users to use a function, then you shouldn't provide it as a public function in the module. And you can control the access by using the special private directive. So here I have a module here. It has 2 variables that are visible to the user of the modules. One is public, which is the default. It's called visible. And we have a private variable called invisible. You can do the same thing with your subroutines. If you don't do anything, all subroutine will be public, but you can specify private, and then you specify the name of your subroutine, in this case, private function here, to make sure that it's not available in the interface to the module. Public, that is the default, which you don't have to, but there is a version of this as well, and then it will provide that function as well. And you declare your subroutine just like you do with normal subroutines in the code. So what I here are two examples here. So in this case, I use my module. I call my public function. Nothing is wrong. But if you try to compile a routine, so in the second example here, I have a private function here. I try to call that. If I compile this routine, you can see here that already when you compile this, compile and link your program, it's not possible to link a program calling a private subroutine. So it's kind of hidden away. It's removed from the public interface of the module, and you can't even link your program. So this is a good way of protecting the internal implementation of your modules by specifying them to be private. Another new concept that has been introduced in Fortran is pointers. It's not pointers in the way in other languages like C++ and C, which is very powerful. You can use them to do anything. Pointers in Fortran always has a reference to a variable or no variable. So it is not possible to kind of reference in empty space in your computer. You need to be able to provide a reference to an existing variable in some sense. It's very strictly typed, so you need to specify the data type of the pointer. And things that you want to point to must have a special attribute called target in the variable declarations, and that is for compiler optimization. So the compiler knows that this variable will be in some point in your code pointed to by a pointer, and if that is not a requirement, the compiler can do optimizations in different ways. That the pointer feature also enables you to return allocatable arrays from procedures, for example. When you don't want to point to anything, you can use the nullify pointer here. That will disconnect the pointer from the target. And you use the equal sign greater than operator to access what is behind the pointer, so to speak. So in this case here, I have created two arrays here, two-dimensional arrays. I allocate A here, and then I can tell, I said here that B will be a pointer to a two-dimensional array, and I also said that A will be a target of a pointer. So I can point things to pointers to A because it has the target attribute, and then B and C will be pointers. So I can associate B with A using the kind of arrow assignment here. B points to A, and then I can use B just like it would have been A. I can also use pass a pointer to a subroutine, for example, create array. And you see here I have create array D here, and it has a input argument here called pointer D, and then I can allocate the array D here, and that will be associated with C in this case. So in this case here, because I allocate and assign a pointer, D would not be deallocated. If this wouldn't have been a pointer, D will be deallocated inside this function here. Then I do deallocate C to free the memory. Then I can also point my B to a null, a special function called null. Now there is no connection with B to A, for example. So if you try to access this B here when there is no association, you will get the same issue that you have with your other code here. In this case, that you will get an access violation or a segmentation fault. Some advanced I/O. I talked a little bit before. List-directed I/O. So it's a specific file format that you can use to write variables, reading and writing variables to files in a bit more structured way than just writing all the values to a file and then reading them back line by line. So in this case here, let's see. Yeah. Sorry. List directed IO. That is the default format to write. And as I said before, Fortran will handle the conversion from floating point to strings. It will also write in a certain format in that file to be able to detect the different data types. So complex numbers are surrounded by parentheses, and strings must be enclosed in comma and double quotes. And you need to specify, if you read, that you specify them in the same format. So if I write this to file here, so this is I open a file here and I write a string to the file, topping in C, and then I read it back again. So if I write to the file, it will produce the following in the file. So in this case here, it will be A and B, 42, 764. There's a string here, so you see here, it starts with a quote, ends with a quote. Then there's a logical value here, topping here, and that is written either as T or F, depending on if it's true or false. Then you have a, let's see here, topping C. C is a complex variable, as I said. So this will be surrounded by parentheses here and the two values in the complex variable. So if you have that in a file, you can read it back again, just like this, A, B, topping C. So Fortran will kind of interpret the things in the line as integers and floating points and strings if you write it in this way. Then there is a more sophisticated way of doing it. So it's more structured than just as the list IO. And then you read and write named values to the file. And you define these names using the name lists declaration. And here you specify all the names that you want to use in the file. And input must consist of the name value pairs. So you specify them like name and then a value, name, value, and end with a /. You can also specify arrays in array, and then you have name equals to 1, 2, 3, and 4, 5. And you can both read them and you can write to this name list IO files. So here I have an example here. We have an integer here with variables I want to write to disk. Then I have a name list here that I called food that lists the variables I want to use and the names of the variables I want to use in this file. So these are actually reference to the variables in your code. So if I do open file here and I read from the file, it will read, and you specify here name list food. Then it will read those variables from the file, and the file will also be required to be have these names in the format that I described before. Same thing, you can write all these variables to a file in a single go just by using name list food. Didn't have an example here. Well, but anyway, they will be specified like this in the file later on, and you can read them back again using names. So this is a way of creating perhaps more sophisticated input files for your code in Fortran. Unformatted IO is when you want to write binary files directly to disk. And this could be for efficiency reasons or precision reasons. You want to actually be able to write the floating point with the full precision, no loss, data loss when writing to text files. You will get a full precision. And when you do that, you skip the second parameter of the read and write statement. You just specify the unit here and the variable. And the variable will be written exactly as it's represented in memory to disk. And if you read or write multiple times, it will move in the file and append all the binary data. So you have to really make sure that you read it exactly back the same order, because otherwise the bitmap for what you read or the data reading in will not fit the variables. As I said before, outputs from unformatted data could be system dependent. So it can be some systems will store data in certain ways, and other systems with different processors will do it in a different way. But you can use it for scratch files and temporary files without any problems. Another type of access that you can use with files is you can have something called direct access files. And that is when you need to access, if you have a large set of data in a file and you want to access it in a random pattern way. So you don't read it consecutively, but you read it in, I want to access the 5th record of this file. You can jump around randomly in the file. And the requirement is that every record has the same size and data structure. And then you can access these records by jumping around in the file. And you also have to kind of set the record size when you do this. So here I have an address book that I want, or bank account I want to write to a data file. So I have account information here as a derived data type. I have defined 2 accounts here, account A and account B. I have a variable here called record size that will store the actual size, and then the size of that record I can query by using the inquire function, and then specify IO length, record size, and then just specifying one of these data types here. And then it will print out a record size, actual number of bytes that is required to store the account data type. And here I just add some stuff to this to these bank accounts, and then I open a file. And instead of sequential here, I use access direct. As I also have to specify the record size of this file, so to be able to jump around this file. And then I just put that I want to replace an existing file. And then I just write here, write record size 1, account A, write record size 2, account B. Those were, so I can actually specify exactly which record I want to write to. And that could be in random order, so I can write 2 and 1 as well. You can also move back and forth in the file using, so when you write, it will jump forward in the file. You can move a pointer as a kind of invisible cursor in your file using the backspace here to go back 1 record. You can rewind to get to the beginning of the file. You can go to the end of the file as well. So that you can use with the record-based, so direct access file IO. So error handling. So Fortran doesn't have any exception handling, so you can't use the same kind of techniques that you would do in Python. So most of error handling in Fortran is done by error return parameters in functions. So most of the functions in Python doing IO, for example, has an error attribute that you can set a specific label as well, so it will jump to that error when it's called. There is also a way of getting the IO stat, for example, as I said before, as a function. So here I have, I open a file here, and there you can specify here error equals to 99. That means that if any error happens, it will jump to the row number 99 or the label 99. And this is the only place where you actually use line numbers in Fortran. So this is an exception. So the only way and only place you should use line number is for error function. So what happens here, if something goes wrong during the open and close here, it will jump to 99 here and print out this. And you can do your own error handling here as well. So error 99 will do that. There is also a IO stat variable that you can set to your own variable, and it will be assigned the error code. So if you don't specify error here, it will not jump to anything. It just will silently fail and will set IO stat value to some not equal to 0. Then there is also additional functions in Fortran which has been added in the recent versions of Fortran. I'm not familiar with this slides.com features. Okay, new features of Fortran. So some of the things that have been added in 2008 and later is some allocatable array extensions. So it's actually not required anymore to use pointers, as I showed before, to pass an allocated array out from a function. So you can actually allocate things and use them as dummy arguments in subroutines. And that was done for efficiency reasons. So this is an example here. When I declare here array intent out in my subroutine, and I allocate it here, you can actually use it here as well. So this was not possible before. Then you had to use pointers to do this. But in the later versions of Fortran, you can do this without any, just like you would have think it would be done. So allocatable intent out like this, allocated inside here, and A here will be allocated inside. So you don't have to do any specific allocation in here to call the so subroutines can do the allocation for you. And for certain cases, for example, if you have derived data types with allocatable arrays, calling a subroutine to initialize your data structures could be a useful thing instead of requiring the users to do all this allocation. Then you can have, for example, a deallocate array subroutine that does the other way around, deallocates the complicated data structure. Allocatable functions, you can do the same thing with functions now as well. So you can do your own allocation statement here. So A equals to create vector 20. So here you can see real allocatable dimension : create vector. And then you can allocate create vector n here, and that will, it should be, it shouldn't be, it should be allocatable here. Okay. But that's possible using a function as well. Allocatable components. So you before Fortran 95, I think you couldn't have done. You couldn't. So in Fortran 95 and older, you couldn't use allocatable in your derived data types. You could have pointers here, but you couldn't have the allocatable statement. This is not now available after Fortran 95. So in 2008, you can do this, which is a powerful concept. Submodules is also something new for Fortran 95, for Fortran 2008 and later. So in Fortran 95, a module must be contained in a single source code file. And that perhaps works in some projects that doesn't have really large modules. But what you can do now is in Fortran 2008 and later is you can divide up a module into submodules. So a set of submodules can kind of implement a single large module. And better to show this here. So in this case here, I have a module points, and I have a submodule points here, points A here. So this is actually, when you implement this, this will actually, the user will only see one module called points, but it consists of multiple files here, consisting of, so you can divide, so it's easier to handle smaller modules than handle multiple or single large module file. Another thing that is really nice, and I will talk about in the next lecture in mixed language programming, is Fortran now has a module for C interoperability. So before you had to kind of figure out which data types actually, which data type was compatible with C in Fortran. And that was not clear because the C and Fortran standards are different, and they define the data types a bit differently. Usually, most of the data types works perfectly, but it's not guaranteed. But there is a new module now called ISO C binding, nice thing with this module is it contains the definition of all the C data types mapped to Fortran data types. That means that you can declare a C floating point variable in Fortran, and you are guaranteed that this data type corresponds to the C version. So in this case here, you can see I use ISO C binding here. And then I can declare in my Fortran code, I can declare this is a C integer, this is a C float, this is a C double. And then I can assign my variables here. I can use of course, my C, the suffix here as well for the data types here and work. And this is also used mostly when you want to link Fortran code with C code and make sure that the data types are the same. But it could be also for if you have the data files you want to write in C and Fortran, and you want to make sure that the data type written to disk is binary readable by C. This could also be an option to use the C interop module then. Another important use of this module is to be able to call C routines, for example, or vice versa, to expose a routine from Fortran that you can call from C. And the requirements of this is actually you can declare the data types in the subroutines directly. For example, in C, the scalar arguments. So if you have single arguments, float A, for example, that's always passed by value. So there is no, in Fortran, that would be passed by reference. And that makes it hard to kind of connect these two languages together. There's also an attribute now that you can declare in your subroutine called value that will actually force Fortran to use pass by value, which hasn't been possible before. So you can create a subroutine that actually passes arguments by value. That is not by pointer, but by the actual value of the passed argument. And that is to make it compatible with C. And if you are careful, you can actually declare a subroutine in Fortran that links exactly to a C routine or to a C program. So you can link them together, combine multiple C and Fortran Fortran source code in a single program and link it together. And you will guarantee that you get the right linkage between the subroutines. This has been really a hard problem to solve before. So this is a very good thing. So another thing that has been implemented and added in Fortran 2008 is object-oriented programming. So up until Fortran 95, you could do modules and you could operator overloading, but Fortran never took the step to becoming a full object-oriented language. And now you can do this. So you can define classes in Fortran. They are called types in this case. So we use the same kind of concept as in modules. So you have type, my type. Here are the attributes in the class. Contains will define which methods goes into the class. In this case here. You can also declare things to be private and public. And then you implement your subroutines here. And you see here, Fortran also uses this notion of self or this. So this is the actual instance of the object that you have implemented. So here you see class type this here to be able to access its own member variables. Then you can assign the different member attributes here using the this and the percent operator my value here. Reset variable, my type variable. So object-oriented programming is possible now. So then you can create an instance of an M type, create an object of a class M type by declaring just like a data type class M type : X. And then you can use call X right here, and then we'll call the write method of the X object here. So fully object-oriented programming is now available in Fortran as well. Another really interesting thing that was not possible before in Fortran was actually to get access to environment variables in your system, or command line arguments for that matter as well. So there is additional functions available now called get environment variable, very simple, where you can query environment variable and get the strings back from the environment variables. There's also a command argument count, which will return you the number of command line arguments to your which your executable was called, and then you have get command argument here to get the actual argument of your Fortran code. This seems like something that should have been there from the beginning, but has kind of been overlooked in the standards here. But now it's available to your Fortran code as well. So before we end here, I will also demonstrate how to use the Qt creator to create Fortran projects as well. So now I'm showing you the screen of the Aurora HPC desktop environment, and I opened a terminal here, make terminal to the system, and I want to be able to develop Fortran code. I need to add some modules here. So I will add module load FOSS 2021A. That will add the compilers I need for Fortran development. I will also need to load the CMake module here for be able to handle the CMake to build things with Qt Creator. If you're on Windows, that is built into the install. I show you, so you don't have to think too much about that. And then load Qt Creator here on the system here. And I Qt Creator. So now I start Qt Creator. So if I want to build a program using Qt Creator, the first thing I have to do is start, create a new project, file, new project. You have to make sure that you specify non-Qt project here, not something else here, and you select My Fortran application. Select, and I do My Fort2. I press. You can see you can specify where you want to locate the project as well. So if you specify it, it will create a directory called myFort2 in my home directory. I press next. Build system is CMake, keep the default. Press next and finish. That will create a default Fortran program. Just prints out hello Fortran, and you can see here it already compiled and built the software or checked the build environment. And you can see now here that I have my source code file main F90 here. So I can build this environment just pressing the hammer here down below. We'll build the code, and there were no errors here. And then I can press play here to run the code. And the output of the code is here. If you want to run it in a standalone module, you can do that as well. You click the project settings and run. You select run in terminal here. And if I run it, go back now again, and I run it here, it will open in a terminal window like this. And for some of the exercises where you have input from standard input, you need to run it in a terminal. Otherwise, it will not get the input. So go into project settings, run, and check this one here. I will run it inside my, go back to editing here again. If I run it now, it will run here. So now the output from the Fortran code is here. I can also do, so I will do a loop here. I'll just check if it builds. Yes. There is a debugger as well built into Qt Creator here. It's start debugging or start a project. So debugger enables you to step through the code line by line. if I just run it like this, it will just execute and run just like normal. It shows on additional screens, so it's not useful in this case. But if I want to see what happens in my code, I can go back here and I can put the set a breakpoint here. For example, click on the line 13 here and put a breakpoint. If I debug my code now, it will stop at that position. And you can see here, it opened several other views here. I have the calling stack here. You can see here that Linux called a start routine. It's called start main in libc, and then it called my main routine here. And then now I'm inside here at this breakpoint. It also shows you the variables now in the current context here. So in this case, as it's undefined currently, it shows you some random value, and it shows a data type here. I can step over my code here by pressing step over here. It's also available here in the code here by step over that will execute the line without going into a subroutine. So now it printed out here, you see here, hello Fortran. And now I can continue running here, step over, it goes into the print statement, prints out 1, goes back like this. And then now I stepped out and went into the operating system. I can also try to continue here to continue and finish the execution. So this is quite nice. The debugger can also, if you have problems in your code, so I will purposely here do something bad. Real compiles perfectly. Let's see if I can get it to crash. Remove my breakpoint here, run it in debug mode. Apparently, it was not enough to crash the program, but let's see if I do something even more stupid. Let's see. I do like this. I create an allocatable array. I don't allocate it. I try to assign a variable to this value. Let's see here, build, still builds. So now you see here, I got a signal segmentation fault here. And that means that I accessed memory outside the program's allocated memory. So you can see here SIG segmentation fault, and the program stops at the line, offending line, automatically. So in this case, so running it through the debugger can sometimes find these kind of obscure bugs. So if I stop the code here, stop debugging, and I can do so allocate A20 like this, and then I run it again, debugging. It should not, so it runs, finish debugging here, and it terminated the program. So this is the way. So if you want to add a file to a project in Qt Creator now, you can do that as well. So then you do new file or project. You create Fortran here. Fortran, let's say a module file here. Choose. I wanted to go into my Fort project here, so I call it my module. Next, finish. So I have a module here, and I will declare a magic variable here. Like that. And then I go into my main program here, and I will do use my module. So now what I now have to do is I have to actually tell Qt Creator here to update my project here, because now I've added a file and it's not visible here, which makes it will not compile. So you need to add it, and you can select this one, right click, and you do run CMake here. And now you see it added the module to my source code file. I will go through CMake more on the next lecture. Also how you use make. Just remember now, if you add something to your project here, you have to click here, run CMake. Then it will update the project here, and now you will be able to build a project as well. And I can probably print out here, print star, what was this called? Magic variable. $42, and then I can print out this magic variable here. So it printed out 42. So this variable here is declared in my module here. I can use, because I have used module here, I can use the variable here, and I can print it out like this as well. So this is how you can use Qt Creator with this extension. So you need to add extensions to this. I have made them available. If you're using a raw user, Qt Creator has this built in, so you don't have to do this. But if you use it at home, you have to follow my instruction how to modify Qt Creator to be able to use Fortran. Okay. I am done for this here now, so I'm